Hello, everyone, and welcome to the Section 1 example problems for the Abstract Modern Algebra lecture series. So we have 10 problems that we're going to look at for Section 1 to work out from what we covered in the lectures. So let's take a look at these problems. So let's start with problem 1. So we have a chemist who's analyzing the chemical compound CH4 or methane, and he wants to know what elements produce the following symmetries for testing. So we're asked to determine the elements that produce the following, and we're also given a hint that CH4 can be represented by the dihedral group D4. So we need to find the element U cubed equals rotation of 180 degrees. So we need to find what element of D4 produces that. And x squared equals a rotation of 0 degrees, y cubed equals a rotation of 270 degrees, and z to the fifth equals the horizontal reflection. So let's look at this. So for the first one, we have x cubed. And if you remember, that's x. And remember, this isn't exactly like multiplying like we would normally think of something raised to a power. It's actually a function composition. So we need an element when composed by itself 3 times, it produces a rotation of 180 degrees. So for all of these, it's best to refer to the Cayley table, which you can refer back to part 1 of section 1, where we went over that to look at the different elements to determine this. It's really just trial, error, and reasoning for this, but you will find that a rotation of 180 degrees, when composed 3 times, produces a rotation of 180 degrees. Because if you think about it, when you rotate something 180 degrees once, it's at 180 degrees. Then again, you're at 360 or 0. Then rotate it again, and you're at 180 degrees. So, and I've been using the wrong symbol for this. This is going to be U. There we go. So we have U is a rotation of 180 degrees. So that's the first element. And then for the second one, we have x squared is a rotation of 0 degrees. Now, one that satisfies this is a rotation of 0 degrees because it's just an identity. However, there's more elements that can produce this. So rotation of 180 degrees composed twice produces a rotation of 0 degrees, or a horizontal reflection twice, or vertical reflection twice, or diagonal reflection twice, or the reflection across the other diagonal twice. So our elements for x are going to be rotation of 0 degrees, rotation 180 degrees, horizontal reflection, vertical reflection, diagonal reflection, and the other diagonal reflection. So this is a set of elements that can produce this. All right, let's look at the third one. So we have y cubed is a rotation of 270 degrees. Well, a rotation of 90 degrees 3 times will give us that. Oops. So y is a rotation of 90 degrees. And then for D, we have Z equals the horizontal reflection. Well, the horizontal reflection 5 times will produce the horizontal reflection. So we have Z equals H. And that's it for the first problem. And I thought for this first problem, it would be nice to see kind of a real life example of this. I don't know if anything like this has ever been done before, but you never know. This might come in handy for chemistry one day. All right, so for problem 2, we are asked to fill out a Cayley table for the dihedral group D6. And we have E, R, R squared, R cubed, R fourth, R to the fifth that describe the rotations. And then we have S, RS, R squared S, R cubed S, R4S, and R5S describe the reflections of the group. And then we need to identify if D6 is abelian or commutative. So the reason that I've used this kind of notation for this problem for the rotations and reflections is depending on like which like textbook you were looking at or which problems you were using, this notation is sometimes used instead of like for D4 we were using a rotation of 0 degrees, rotation 180, and then horizontal, vertical, and everything like that. But it makes it simpler too, especially when you get into much bigger dihedral groups to use this kind of notation. So this was a table that I made in Excel and copied in here. So we should be able to type in these boxes to figure out the missing elements for this Cayley table. And the way you would figure out this Cayley table is you can either logically reason it out by doing the composition. So this would be R cubed composed into R cubed. Or sometimes with these Cayley tables, you can notice a pattern for some of these elements, and you can use that too. But this one's pretty simple. R cubed composed with R cubed. Well, that's just the identity element, E. All right, let's see. So we are filling in, the next box we're filling in is for R squared S composed in S. So we can probably just logically reason this one out instead of getting our heads spinning around with the rotations of a hexagon or whatever D6 group this is. So sorry, Hector the hexagon from lecture 1, but we're just going to do a pattern here, and it's going to be R to the fourth for this one. This is our next box here. We have R to the fifth composed in R cubed of S. Again, you can just observe the pattern here. That's going to be, we'll just copy and paste this so I won't have to type it, R to the fourth of S. And then for the last one, which is right down here, we have R to the fourth of S composed in R to the fifth of S. Well, that's just going to be, I can actually type this one out, R. Okay, so this is our Cayley table filled out. So to identify if the group is abelian for every single element, it must be commutative. So if we find a counterexample to this, then it is non-abelian, and there in fact is a counterexample that we can spot from this table. So we have R cubed S R4 equals R5S, and I'm going to circle that right here. But does R cubed S R4, does that equal R4 R cubed S? Well, let's take a look. Let's go to R4 and then scroll over to where r cubed s is. This is where we are. So r4 r cubed s equals rs. So no, they are not equal. So r cubed s r4 does not equal r4 r cubed s. So D6 is non-abelian. All right. And that's everything we need to do for this problem. So we will move on to the next problem. All right. For problem 3, we are asked to describe the symmetry group of the two pictures. So let's take a look at these two pictures here. We have a little plant, leaf, and a star. These were some I made in Microsoft Paint, so they may not be perfectly symmetrical. I'm sure the star is symmetrical, but maybe not the leaf. But to identify the symmetry of the group, let's take a look at the leaf. It has 1, 2, 3, 4, 5, 6, 7 leaves. So this will be dihedral group D7. And for the star, 1, 2, 3, 4, 5, it's a dihedral group D5. And this leaf is actually based off of a real plant. I don't have the name of it on me right now, but you can look it up online, and it's a leaf that's a 7-shaped leaf. So, some of these you can actually see in nature. So, all right. Well, that's all there is for problem 3. So let's go on to problem 4. So we are asked to determine if, let me fix this, the following sets are closed under the given operations. So the first one is the set S, which has the elements 0, 8, 12, 24, and it has an operation of the addition modulo 6. And then B, we have the set T with elements 0, 3, 7, and 11. And it has the operation multiplication modulo 8. So let's figure out if these are closed. So we have S addition modulo 6. So A, B, and A plus B must be an element of S if it has this operation. So let's take a look at the elements here. So we have 0, that's the identity, because you can add it with the other elements and it'll produce an element that is in S. So let's go on to 8. 8 plus 8 equals 16, which is 4 mod 6, because if you remember what congruence of integers is, it's basically the 6 is divisible by 16 minus 4. So 8 plus 12 is 20, and that's 2 modulus 6. And then 8 plus 24 is 32, which is 2 modulus 6. And then 12 plus 12 equals 0 modulus 6. And then 12 plus 24 is 0 modulus 6. And then 24 plus 24 equals 48, and that's 0 modulus 6. So let me put logically equivalent, because That's generally what you do for congruence of integers. Okay, so I think that's all the addition operations we look at with these elements. So what we have is 0 to 4 with this operation, but 2 and 4 are not an element of S, so S is not closed under addition modulo 6. All right, now let's look at part B. So we have T with the multiplication modulo of 8. So A, B, and A, B need to be an element of T. All right, so we have 0, and again, that's going to produce 0 for anything it's multiplied by. And we have 0, 3, 7, 11. Those are our elements. So we have 3 times 3, that's 9, which is logically equivalent to 1, modulus 8. And then 3 times 7 is 21, which is 5, modulus 8. And then 3 times 11 is 33, which is 1, modulus 8. Then 3 times, we have 7 times 7 is 49, which is 1, modulus 8. And then 7 times 11 is 77, which is 5, modulus 8. And I keep forgetting that we describe these as being logically equivalent. And 11 times 11 is 121, which is logically equivalent to 1, modulus 8. So what we have from this operation is we have the set 0, 1, 5. But 1 and 5 are not elements of T. So T is not closed under multiplication modulo 8. Yep. All right. So that's problem 4. Let's move on to problem 5. So we are asked to determine if the following sets are groups under matrix multiplication. So the first one we have is G, which is described by the matrix, the 2 by 2 matrix A, B, C, and D, where they are elements of Z, of the addition modulo group, of the group of integers with addition modulo 7, and the determinant is not equal to 0 modulus 11. And then H is described by the same 2 by 2 matrix, but these are all rational numbers, and the determinant does not equal to 0. So let's take a look at this. So let's take a look at the first one. So since A, B, C, and D are elements of integers with addition modulo 7, the arithmetic is mod 7. So for matrix multiplication, the determinants to, these matrices need to be equal to each other. So equal to their individual determinants. So the determinant of A cannot be equal to 0. Or excuse me, that's not right. So if A and B are elements of G, then the determinant of A could equal 0 modulus 11, or the determinant of B could equal 0 modulus 11. So closure fails. And this means G is not a group. And the reason this is because we have addition under modulo 7. So the elements could potentially be 0 modulus 11. All right. So we don't need to go any further with that. We'll go on to part B. So let's have A and B be an element of H. Then the determinant, these two multiplied, is equal to their individual determinants. So the determinant of A cannot equal 0, and the determinant of B cannot equal 0. So therefore, AB is an element of H since they are not equal to 0. So yes, this group has closure under its operation. But before we can conclude that it's a group, we have to check the elementary properties. So start with associativity. So let's let A, B, and C be elements of H. So A times BC is equal to A B times C. And this is true for matrix multiplication. So we have associativity. And then see if we can find an identity. So let's let I be the identity of this group and be defined by this matrix. And since I is irrational, because remember that's the set that we are defining the elements of the matrix by, then the determinant of I equals 1 times 1 minus 0 times 0 equals 1. And of course this is not equal 0. So I is an element of H and we have an identity. Now let's check for an inverse. So let's let A be this matrix A, B, C, D. So then we have an inverse of A is equal to this is the formula for an inverse of a matrix where A, D, and where the determinant is not equal to 0. So A negative 1 is an element of H. So therefore, H is a group. Let me try to fix that diamond. All right. So that's it for problem 5. So let's move on to problem 6. So we are asked to prove that the group U14 only has one identity element. So what is the identity element? So for the proving this, let's write out a proof strategy. So we don't need to look at all elements of U14 and can instead prove this using arbitrary elements E and E prime. Trying to make a better diamond there. I've never been too good at drawing these. All right, so let's write out our proof. So let's let E and E prime be identities of U14. Then E of A equals A, where A is an element of U14 and E of A equals A. So E prime of E equals E, and E prime of E equals E prime. So hence E equals E prime. So the identity elements equal each other. So therefore U14 has only one identity element as desired. And essentially the way that this was proved was since E of A equals A and E prime of A equals A, then they're equal to each other, which we can then deduce that, when the identities multiply by each other, they'll each produce their own identities, which means that they're equal. And this is going back to one of the theorems that we covered in the lectures too. So now let's determine the identity element of this group. So we have U14 is the set of elements where the greatest common divisor of an element of the group, and 14 is 1. And of course, let's define what A is. It's just an element of U14. So since two divides 14, let's actually rephrase this because we're trying to find the elements of the group, so it would technically be part of the integers under the addition operation. So since 2 divides 14 and 7 divides 14, 2, 4, 6, 7, 8, 10, and 12 are not elements of the group. So U14 is equal to basically the prime divisors of 14. So we can just try these elements out, but I'll go on and write out what the identity is, since 1 times A equals whatever element you're multiplying by for all A that is in the group U14. Then 1 is the identity. So for this group, we proved that it has a unique identity and then found what that identity is. All right, let's go to problem 7. So we need to perform the following operations. We have GL2 with the set of integers and under the multiplicate or addition modulo 8. And then we have a determinant of the 2 by 2 matrix 11, 1, 11, and 9. And then we have a GL2 of the irrational numbers, and the determinant is 4 over 5, square root of 7, 7 over 11, and square root of 8. GL is, can't remember if I covered this in the lectures or not, but it's just basically a general linear group of matrices. So let's perform these operations. So let's start with A. So we have the determinant of 11, 1, 11, and 9. Well, let's use the determinant formula, and that's basically cross multiplying and subtracting these two. So 11, 9 minus 1, 11. That's equal to 99 minus 11, which is 88. And 88 is logically equivalent to 0 mod 8. So the determinant is logically equivalent to 0 mod 8. And that's the answer of this operation. Then let's go to part B. So we have the determinant of 4 over 5, square root of 7, 7 over 11, and square root of 8. So again, do the same thing as before. We have 4 over 5, square root of 8, and then we have and square root of 7. So the determinant is equal to 4 square root of 8 over 5 minus 7 square root of 7 over 11. Yep, that's all there is to this problem. All right, let's take a look at problem 8. So we are asked to prove that if A and B are elements of a group G, and B is the inverse of A, then AB is equal to A raised to the power of NB times E. So let's prove this. So we're going to let A and B be elements of G, and B be the inverse of A. So then we have AB is equal to BA, which is equal to E. So AB is equal to the identity element E. So now let's let A of N be an element of G, where N is an integer. So then the inverse of A of N would just be A to the negative N. So A raised to the N of B would be equal to A of N times A negative N, because remember, we define B as the inverse of A. So we would have A of N minus N would be equal to A of 0, which would be 1, which would be the identity element. So therefore, A raised to the N of B equals the identity element as desired, because we showed that both AB and A raised to the N of B was equal to the identity element, so we have proved this. All right, problem 9. Let's find the inverses of each elements with the given operations. So we have 7 and 21 of U32. Then we have n plus 4 in U of n squared minus 16. Then we have 6, 9, and 14 of Z19. All right, so let's start with the first one. So we have U of 32, and I'm just going to write out what that set is to make this a little bit easier. Because it's just all of the prime numbers in the set. I don't know if you can see that or not, so let me do it down here. So the inverse of 7 is going to be where 7x is logically equivalent to 1 mod 32, and x has to be an element of U32. So this is basically trial and error. You just have to try the values of u32 to find the inverse. So one thing, I'll go on and just make this simple and show what the inverses are. So when you multiply 7 by 23, that's 161, which is logically equivalent to 1 mod 32. So the inverse of 7 is logically equivalent to 23 modulus 32. And then we'll do the same for 21. After you do some trial and error, you'll find that 21 times 29 is equal to 609, and that's logically equivalent to 1 modulus 32. So the inverse of 21 is logically equivalent to 29 modulus 32. All right, that's the first one knocked out. Now let's do the second one. This one is a little bit more challenging to understand, but we have n squared minus 16. Remember, that splits in, that's a perfect square, so we have n minus 4 and n plus 4. So u of n squared minus 16 is going to be equal to the set of a, where a is an element of the set of integers with addition modulo n squared minus 16, and the greatest common divisor of a and n squared minus 16 is 1. So obviously this is technically an infinitely large set. So we are looking for where n plus 4. I'm not going to write the whole set out, but I'll just leave that definition there to understand what it is. We're looking for where that's 1 modulus n squared minus 16. So probably just need to logically deduce some things and try some things out, but this is one thing you can try, and that's negative n plus 4 squared, which is negative n squared plus 8n plus 16. And then we can determine if this is what we're looking for by breaking it up into, let's look at n squared plus 8n minus 16, and that we can do some algebra here. Equal to n squared minus 16 plus 8n plus 32, and then we have n plus 4 squared is logically equivalent to 8n plus 32 modulus n squared minus 16, and then we have negative n plus 4 squared is logically equivalent to 8n plus 4. And since this is a multiple of n squared minus 16, congruence is confirmed. So I'll just erase all this because I didn't space out these problem statements correctly, but hopefully you understand the reasoning behind this, so we will just write this out as negative n squared plus 8n plus 16 is logically equivalent to 1 modulus n squared minus 16. So an inverse for n plus 4 is negative n plus 4 modulus n squared minus 16. All right, and then for part C, I may have to move some of this over to the side and try to cramp this in. We have integers of addition modulo 19, and that's equal to the set of 0, 1, 2, so on and so forth, up to 18. So likewise, what you had to do with part A, you just had to find where something multiplied to give you 1 modulus 19, and that variable x needs to be an element of z19. So by doing this, I'll go on and just write the answers out. The inverse of 6 is 16. And the inverse of 9 is 17. And the inverse of 14 is 15. All right, that's problem 9. All right, now for the last problem. Once I get a good diamond going, there we go. I probably don't need to include this every time, but I just think it's a good idea to practice it. Okay, so let's go on to problem 10. So we have R and F be any fixed rotation and any fixed reflection of a dihedral group, respectively, and we're asked to prove that R raised to the n composed with F is equal to F composed with R raised to the negative n, where n is an integer. All right, so for this problem, we will have to use proof by induction, because generally when you have things that are raised to a power that are equal to each other, you generally want to use induction to prove it, because I can prove for all the powers raised to it that they're equal to each other. So we're going to let R and F be a fixed rotation and fixed reflection of a dihedral group. And let's let R raised to the n of F be an element of a dihedral group where n is an integer. So we will proceed by induction on n. All right, so let's establish our base case. So we're going to let n equal 1 then r raised to the 1 of f equals rf. So rf equals f times r to the negative 1. And this comes from properties of reflections and rotations of dihedral groups. So the base case is established. All right, so now that we have our base case, let's do our induction step. So let's suppose that RKF equals FR negative K, where K is an integer. Let me write that down here, where K is an integer. So then we have R K plus 1 F equals R times R raised to the K. I'll write it like this, R K F, which is equal to R F R negative K, which is equal to R F R negative K, which is equal to F R negative 1 R negative K, which is equal to F R negative K plus 1. So therefore RK plus 1 F equals F R negative K plus 1 as desired. Oops. Let's get my square drawn out here. There we go. All right. Hey guys, thank you so much for watching, and hope you enjoyed this video and this lecture series for section 1 of the abstract modern algebra. So yeah, that's it for section 1. So I will see you guys in section 2.